Welcome students to lecture number 2 of the MOOCs course on advanced probability theory. In the last lecture, we were talking about events, any subsets of omega. For illustration, again consider throwing a die and suppose A is the event, outcome is odd number, B is the event, outcome greater than equal to 4, and C is the event, outcome divisible by 3. So, if this is my omega, then we can see that this subset of 1, 3, 5 is giving us the event A, this subset is giving us the event B, and this subset is giving us the event C. Therefore, if a set omega has n elementary events, there can be 2 to the power n many different subsets, and each one of them represents some event. Often, to compute the probability of an event, we may like to combine some other events and join them through union, intersection, and complementation to get the desired event. For example, what is the probability that one trial of a die produces a number that is even and multiple of 3. So, let A be the event, outcome is even and multiple of 3. Let A1 is equal to outcome is even, which means essentially 2, 4 and 6, and A2B outcome is multiple of 3. Therefore, the outcome is 3 or 6. Therefore, we can describe A as the intersection of A1 and A2. On the other hand, what is the probability of A1? So, A1 is equal to the union of 3 elementary events, outcome is 2, union outcome is 4, union outcome is 6. Therefore, to obtain the probability of the event A, we may look at the probability of the 3 elementary events, that 2, 4 and 6. Therefore, probability of A is equal to probability of 2 union probability of 4 union probability of 6. Similarly, if A3 is outcome is an odd number, then A3 is equal to A1 complement. Thus, the set operations union, intersection and complementation are part and parcel of defining events on some omega. As I said in the last class, to handle them we need the concept of sigma field. We will often write it as sigma field. Given a set X, a sigma field, let us call it S, defined on X is a collection of subsets of X such that X belongs to S if A contained in X belongs to S, then A complement belongs to S, and 3 if A1, A2, AN so if A1, A2, AN is a collection of finite or countable number of subsets of X, then union over I A I also belongs to S. So, once a collection of subsets of X satisfies these above properties, we called it a sigma field. Some immediate results: phi belongs to S. Why? Since X belongs to S, therefore, X complement belongs to S. X complement with respect to itself is phi. B. If A and B belong to S, then A intersection B belong to S. This is not so obvious because we have talked about union, but here we are saying that A intersection B also a member of X. Proof: since A and B belong to S, A complement and B complement belong to S. Therefore, A complement union B complement belong to S. Therefore, we know that A complement union B complement is A intersection B complement. Therefore, since A comma B belong to S, therefore, A complement and B complement belong to S. Therefore, A complement union B complement belong to S. Therefore, A intersection B complement belong to S. Therefore, its complement, that is A intersection B, belong to S. This can be extended to countable intersections that is, if A1, A2, A3 up to An, n goes to infinity, is a collection of subsets of X which belong to S, then the countable intersection also belongs to S. It is very clear the concept of sigma field allows us to define different events from the set of elementary events whose outcome constitute omega. Question is, how to obtain their probability? The key concept is the concept of measure. Definition: given a set X and a sigma field S defined over X, a function mu from S to the real line is said to be a measure if 1 mu a greater than equal to 0 for all a belonging to S, 2 mu phi is equal to 0. We all know that phi is a member of S, and 3 mu of A1 union A2 union AN is equal to sigma of mu AI, I is equal to 1 to n, if AIs are mutually disjoint. That is, any two AIs if we take, then they have no intersection. For example, if this is my A, this is my A1, this is my A2, this is my A3, this is my A4, like that, we can see that these are all disjoint subsets of X. Probability measure. A special type of measure is said to be a probability measure if probability of the entire set is equal to 1. So, let us define any sigma field over omega, let us call it S, let us define a probability measure P on S, that is P of omega is equal to 1, P of phi is equal to 0, P of A1 union AN is equal to sigma P of AI, I is equal to 1 to n when AI is a disjoint then the triplet omega S and P is called a probability space. And when a probability space is defined, we can obtain the probability of an event through its measure. Note that the event has to be a member of the sigma field, because if you define an event in such a way that it is not a member of the sigma field, then we cannot assign the measure through the probability measure phi, and therefore, we are not able to assign the probability to that particular event. Now, how the sigma field is defined is very important. Because the probability of an event will depend upon the sigma field S. Let me give an example. The example is called Barton's paradox. Now, what is a paradox? Now, paradox is a seemingly absurd or contradictory statement which may prove to be true or well founded when investigated. Question is, how can a mathematical statement be a paradox? Obviously, it will appear to be a paradox if the same problem has more than one solution which are different but at the same time are mathematically correct. So, let me introduce the problem. Suppose there is a unit circle So, let us assume that this is a unit circle and there is a equilateral triangle inscribed in it. Consider an arbitrary chord of the circle. Say something like this or something like this. It is clear that the length of the green chord is greater than the length of each side of the equilateral triangle inscribed in the circle. On the other hand, the length of the red chord is smaller than the length of each side of the above triangle. Question is, what is the probability that the length of the chord is greater than the side length of each side of the equilateral triangle. That is the question. Since it is a mathematical question, it should have only one answer. But we shall see that we have at least 3 different answers, all of which are correct. How can it happen? This will happen because we shall consider different sample spaces to compute the probability. Hence, it is a paradox. Okay. So, let us now look at solving the problem using different sample space that is different set of points and or different sigma fields defined over them. So, here is the solution 1. So, solution 1. So, we have this circle, we have this equilateral triangle, let this triangle be ABC, and we are drawing a chord. It is obvious that suppose we assume one end of the chord is at a point A, then if the end of the chord is in the arc A to B, then we can see that the length of this chord is less than this side of A. Similarly, if the chord is other end of the chord is any point on the arc A to C, then also its length is going to be less than this side of the triangle. On the other hand, if the other end of the chord is on the arc B to C, then we can see that its length is going to be bigger than the side of the equilateral triangle. Therefore, probability length of chord greater than length of side of the triangle is equal to a probability measure of the arc BC over the measure of the circumference of the circle. We are dividing by this p because if we consider the length of the circumference, this is going to be 2 pi, which is not 1. To make it 1, we need to divide everything by 2 pi. This is equal to 1/3 of length of circumference divided by length of circumference, which is equal to 1/3. You have to understand that we have fixed one end of the chord at one of the vertices of the triangle. Therefore, any arbitrary triangle, equilateral triangle that you take, we can always see that the same thing is going to happen, and therefore, probability of the event is going to be 1/3. Solution 2. So, again as before, I draw the circle. This is the center of it, this is a radius, consider this equilateral triangle. Now, we want to draw a arbitrary chord. Note that each chord can be characterized by its midpoint. Because if we take any chord and we draw a perpendicular from the center to that chord, it is going to intersect it at the midpoint. Now, we also know that this radius will be bisected at this point of intersection. So, corresponding to this radius, we can say that the chord will be of length bigger than the side of the equilateral triangle if its midpoint is somewhere above the point of intersection, and the length of the chord is going to be smaller than the side of the radius if its intersection with the radius is somewhere below this point. Therefore, probability chord length is greater than side of equilateral triangle is equal to length of this radius, half of the length of the radius divided by the total length of the radius. Is equal to. This is because we have taken the sigma field as points on the radius. Let me give you a third solution, very similar setup. So, here is the radius, here is the midpoint of the radius, which is at a distance half from the origin. So, consider this concentric circle. We say that the length of the chord will be greater than side of the equilateral triangle if the midpoint of the chord falls somewhere inside this circle. So, if this is the midpoint of the chord, then I will draw the radius like this, and then I draw the perpendicular through that one. So, that is the chord we are looking at, and obviously, its length is going to be bigger than the side of the equilateral triangle. Midpoint of the chord is inside the circle C. So, let us call it C. Therefore, probability chord length greater than side of equilateral triangle is equal to the measure of this circle, which in this case we can write as area of C divided by area of unit circle, which we know that is going to be pi half square upon pi is equal to 1 by 4. Thus, we see that depending upon the interpretation of the sigma field, we are going to get different answers in different cases. In the first case, we were looking at the sigma field to be points on the circumference and the length of those arcs. In the second case, we are looking at the radius and the points on each radius, and in the third point we are looking at concentric circles and we are looking at the points inside it. Thus, what I wanted to emphasize on is that depending upon how you define the sigma field, the probability of the event may change. Therefore, we need to be very careful about defining probability when things are complicated. Problem: suppose we choose a random point from the square zero to 1 cross 0 to 1. What is the probability that the x and y coordinates of the point are same? So, that is the question. So, for our understanding, consider the xy plane and suppose this is the square that we are talking about, and we are looking at the probability that the x and y coordinate of the random point are same. So, for example, if I choose this point, obviously the x value is very small, y value is very high, and they are not same. It is very clear that the x and y coordinates will be same if the point is lying of the line, this diagonal of the square. So, probability of the event, so let us call the event A. The probability of A is equal to measure of the line AC over measure of the square ABCD. Now, square ABCD is two dimensional. Therefore, a meaningful measure is its area. The line AC is one dimensional. Therefore, one possible measure could be length, but then length of AC divided by area of ABCD has no meaning, because they are two different units. Hence, we need to consider the area under the line AC, and we know that area of AC is equal to 0. Therefore, probability of the event A is equal to 0 upon area of ABCD, which is 1, is equal to 0. A very similar question. What is the probability that the random point has x coordinate greater than y coordinate? So, again if we look at the square, and we can see that if this is this diagonal, then for each point in this triangle, the x value is greater than the y value. On the other hand, if we consider this triangle, for each point inside, the x value is smaller than the y value. Therefore, probability of this event, let us call it B. Probability of B is equal to area of this triangle, let me call it OMN divided by the area of the square MNPO is equal to half, because the area of this triangle is going to be half, area of the square is 1, therefore, this probability is going to be half. So, I hope now you understand how we use measures for computing probability of an event. Let us now summarize. The discussion. Let T be a random experiment. Let omega be the set of possible outcomes. Any subset of omega is called an event. Omega may be discrete or continuous. When discrete, probability of an event is equal to number of favorable outcomes divided by total number of outcomes if omega is continuous, we need to define suitable measure to compute the probability of an event A as measure of A, if we call it by P, by measure of omega. Typically, we keep P of omega is equal to 1. So, if this is 1, then P of A itself will give us the probability of A. If it is not 1, then we have to make the division, and therefore, through that we will get the probability. Omega S, where S is a sigma field over omega, is called a sample space. The triplet omega S P is called a probability space. To obtain probability of an event, A has to be a member of S. The sigma field allows us to obtain probabilities for different events constructed from complementation, countable, union, and intersection of more basic events. Okay, friends, I stop here today. In the next class, I shall start with Kolmogorov's axioms on probability, and also we shall look at certain different mathematical functions which will lead us to define certain probability of events. Okay, friends, thank you so much.